तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
In the last lecture, we developed a methodology to design a sequential circuit. Actually, we took a simple example of a sequential circuit, a circuit meant to detect a pattern 0 1 1 0 from a serial bit stream. For this circuit, we developed the state graph. This was the state graph we got, and then we assigned, there are 4 states in this, so I assigned state variables as A and B and assigned these values to this A and B as given in here, S0 0 0, S1 0 1, S2 1 0, S3 1 1. There are only 4 states. The input bit stream we indicated by X and the output Z, and whenever a pattern 0 1 1 0 is obtained, Z, the output, will be 1 corresponding to the last bit of the pattern, and we also and all other times Z will be 0. We also said there is an overlapping pattern. That means if another 1 1 0 occurs, this 0 would be taken as the first bit of the next pattern also. So anyway, this is a simple review because this is sequence circuit design has already been would have been exposed to you in your previous course in digital systems, but in order to keep the flow and to define some of the underlying concepts, we took this simple example. But since the focus of this lecture series are more on implementation using ICs and final ultimate implementation of IC systems, VLSI systems, so we would not like to do a gate level implementation of this circuit. That is what we did in the last lecture. We took a couple of flip flops. The flip flops A and B were driven by circuits involving gates. We went through the corner map reduction and all that. That is a normal procedure. As I said, it is more of a review. But when you do a design for a IC design, we will use more and more complex hardware, or more let us say hardware with more functionalities to replace gates, so that the design becomes simpler. So today we will see some of the mapping techniques of implementing this circuit using MSI components in the combination logic. The combination logic will be replaced, the gates of the combination logic will be replaced by components such as multiplexers, ROMs and PLA, and that will be the focus of this lecture. So anyway, we have to get the state table. We already got it in the last lecture. We will rewrite it now. The state table, the present state, variables are A and B, as I said, input is x, next state variables output z, and there are 4 present state S0, 0, 0, then S1, 0, 1, S2, 1, 0, S3, 1, 1, and from this state table, from this state graph we can write the state table. We already did it last time, again we will redo it. If x is 0, what happens in the next state and what is the output? X is 1, what happens? Likewise we do for S1, S2 and S3. So, without spending a lot of time, since we already have done this exercise, I can write this as 0, 1, 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 0, 1, 0, 1, 1, 0, 0, 1, 0, 0, 0, 0. Oh, this is a 1, output is a 1. This is the next state table, next state and the output information correspond to the present state and input. This is the same table which you got last time, or you can also simply get it from here. For example, if your state is 0, input is 0, output is also 0, and the state goes to the x1 which is 0, 1. So, 0, 0, 0, 0, 1, output 0. Like that you can do all the 8 rows. And now instead of going through the reduction using corner maps as we did in the last lecture, using gate implementation, I am going to straight away say that I am going to use multiplexers as combinational building blocks. So, since we already saw the implementation of combinational logic using multiplexers, we should be able to easily fit in. We know that any combinational logic with the definition of the input output relationship can be implemented using an appropriate number of multiplexers. So, let us try to do it here. So, it is a simple procedure here. Since there are 2 states, there are 2 flip flops, that fact is not going to change, whether it is a gate oriented design or a mux oriented design or a ROM oriented design or a PIL oriented design. It is not going to change the fact that 4 states require 2 flip flops. So, let us call these flip flops A and B as we have done here in this case. So, this is flip flop A, output is A, flip flop B, B. So, Q is A, Q bar is A bar. Similarly, Q for this flip flop B, Q for B bar. The D of this flip flop we will call it DA or A plus. The next state of information will be the for a D flip flop, the output follows the input. That means, if you give the next state information here, that will be taken as the present state when the clock arrives. That's why we call it A plus. If you want to call it DA, this is fine. Similarly, call this D and P plus driven by a common clock. This is required for the 4 states. For 4 states, we need this type of 2 flip flops working. Now, the question is, the 4 values of A and B 0, 0, 0, 1, 1, 0, 1, 1 will occur based on the present state and the input given. That information has to be given to these inputs of this flip flop DA and DB, only then they will change state accordingly. Who is going to give that input? In the previous design, the combinational gates is responsible for giving this, gates are responsible for giving that input. In this case, I am going to make multiplexers give that input. So, what I am going to do is to put a multiplexer here, another multiplexer here, And what is the size of the multiplexer? The size of the multiplexer is decided by the number of different outputs, different inputs this will have. Now, there are going to be 2 state variables, that means there are going to be 4 combinations of inputs. For each combination input we should decide the next state. So, if you have 4 to 1 multiplexer here with 2 control lines, for each of the 4 states 0 0 0 1 1 0 1 1, we can find out the next state. So, the next state information A plus for each of the present state information will be given in from a 4 to 1 multiplexer. So, the size of the multiplexer is decided by the total number of states in the circuit we are designing. In this case, the total number of states in this circuit is 4, so I need 4 to 1 multiplexer. If I had total number up to 8, I should have 8 to 1 multiplexer, and so on. Likewise, for the second output dB or B plus, if you want to call it B plus or dB, it does not matter. The present state information S0 and S1 will give the corresponding next state based on the input condition. Again, I will have 4 choices of S0, S1 for 4 different states, and each of these states will correspond to an input condition which will be the next state. Now, that means I will have this I0, I1, I2, I3. And S0, S1 are the present state variable. Present state variable with a given input condition gives you the next state outputs for these 2 multiplexers. How do I get this present state information? The present state information is available in these 2 flip flops. So, I need to connect this S0 to A, and this is S1 to B. So, it is nothing but S0 is nothing but the state variable A, and S1 is nothing but the state variable B. So, now look at the table here. AB 0 0, 0 1, 1 0, 1 1. For each of these conditions, I will take the appropriate input of the multiplexer and see whether the input is connected to x is equal to 0 or x is equal to 1. Based on that, the next state will be decided, because next state will be decided in the present state and in the present state based on the input condition x. For example, if you take S1 is the present state 0 1, I will not be able to decide the next state unless I know what x is. So, that what x is will have to be, this information have to be given, and that will be given through these inputs to the corresponding, for that corresponding state. Now, it is a very simple procedure. You look at the input condition 0 0. If the present state is 0 0, what is the next state? The next state is for flip flop A. We are talking about flip flop A first. Multiplexer A corresponds to flip flop A, multiplexer B corresponds to flip flop B. Let us look at the multiplexer A to start with. For the present state 0 0, the next state A plus is decided by the input. If x is 0, the output is 0. The next state is 0, x is 1 also, the next state is 0. That means irrespective of the input, the next state of the flip flop is 0. So, I put a 0 here. You go to the next, the present state is 0 1, that is the corresponding combination is 0 1, A S1 corresponds to 0 1 combination, corresponds to this input I1. In this case, the present state is 0 1, the next state of the flip flop A depends on the present state. If the present state is 0, the present state 0 1, the input is 0, the next state of the flip flop A is 0. If the present state 0 1, the input of the present state, input of x input is 1, the next state condition of the flip flop is 1. So, that means in the present state 0 1, the output of the next state A plus is decided by the present state x. If x is 0, this is 0, if x is 1, this is 1. That means connect x to this. If x is 0, this will become 0, x is 1, this will become 1. In the previous case, whether x is 0 or 1, this should be 0, so I put a 0 here. Moving on, for the present state 1 0, which is S2 condition, I2 input. The next state of flip flop A is resolved by again x here. If x is 0, the next state of the flip flop A is 0. If x is 1, the next state of the flip flop A is 1. So again it is same as x, it follows the x. The last case, irrespective of the flip flop condition, in the last case S1, S3, 1 1, irrespective of the input condition 0 1, the next state of the flip flop is 0, so I put a 0 here. This is how you design the combination logic which will drive the flip flop A. Now without having to go through so much explanation, since we already done it for one case, I can write simply for the second flip flop is x bar will make it. When x is 0, the next state is 1, x is 1, next state is 0. So it is x bar input, same here. In the third case, present state S2, the next state is 1, irrespective of x is 0 or 1. So it is a 1, and again x bar. So this is an x is a very simple input. Now I can replace this by a, I can leave it as, after all x is the input that is available to you, x bar can be gotten from x from a using an inverter. I do not have to show it in this drawing. Yes, you have a question?
S0, S1, AB, should it not be interchanged?
No, you use S0, S1. No, this S is a selector S. Right?
Once you say 0, 1.
0 0, 0 1, 1 0,
AB
1 1.
0, 1.
Yeah.
Second input is selected.
No, sir. Traditionally, S1 S0 there.
S1,
So
S0.
that's what it
MS3 must be there.
is. S1 is a.
No. This S0 and S1 is only selectors. You want to interchange there? That is okay. That is only a convention. Yeah, if you want to call it S1, S0, fine with me. See, this S, I am sorry, I should have really not used S1, S0 because this S is a state variable, state S0, state S1, state S2, state S3. These are selectors. So since S is same for state and selector, there is a confusion here. This is not a big issue here. It's a convention. The convention is the highest, the MSB, LSB convention. It is not affecting the design in any way. The connections have not changed. All you are telling is I should have put S1 and S0, not S0, S1. Actually, I should not have used S at all because it is confusing. S is used for selectors as well as for states. Maybe I should have used some M0 or M1 or something like that. Whatever. That's fine. Now, as long as you understand, these are the selector inputs. Actually, there is no need for this. S0 is even by a multiplexer. They will be like this. That's all. They won't tell you anything. Of course, there will be power supply. If you leave power supply out, if you leave the power supply out, there are going to be so many pins. These are the input pins, these are selector pins, this is the output pin. We designate this as S1 and S0, I0, I1, I2, and F. So designations we give for these pins. That is why this S1, S0 came here, because these are selector pins, these are input pins, this is an output pin. So because of that, we got this S1, S0 interchange, but not to be confused with the S0, S1, S2, S3, because this S, we are not using it as in the equation, this only to indicate the condition. So if you do not like this S0, you say state 0, so that you can completely avoid that confusion. There is no conceptual or design variation here, it is only a convention. Is that all right?
No, Mux actually, this S1 denotes the LSB and MSB. And
Yes, that is only a convention we are discussing. We are not making any design error. Are we making a design error? Let us not discuss the convention. Of course, the convention is there in the book. Yeah, I know, I understand. That is why I explained all this very clearly now. The convention is S1, S0. That is why you pointed out. Well taken. I have changed it. but we will drop it because I do not want to confuse this viewers of this lecture that it has something to do with the design. No, it has nothing to do with the design. Design is correct and my connections are right. That is the gist of this thing. Of course, convention also have to be respected, and I respect your the convention as well as your sentiments. Thanks you. Thank you. Okay. Now, the output side, there is only one output of 1 and all others are 0. That output comes when the input is 0 1 1 with an input 0. So, it is nothing but Z can be written as output Z can be written as AB x bar, correct. So, since x bar is available here, you put AB A B this is my output C and x bar is here. All I am saying is you take this x as input to system, connect it here, same thing will become x bar, and this is my 1. This is the design. There is only one input, one output, one input, one output, because after all my system finally should have this type of a box, one input x, one output z, one clock. So, age triggered clock, I put it like this. So, this is my this box here is the unknown system which we designed it using this. This x corresponds to this input, this z corresponds to this output, this clock is this clock. That is all. Otherwise, the zeros and ones are 1 is a VCC, 0 is a ground, and output comes here into the flip flop. All this is part of the design. This is how we design. This is a very simple design for two reasons. Reason 1, this part of the circuit is same. Any circuit up to 4 states, any design up to 4 states will have the same 2 multiplexer architecture. Only things will be different, only things that will be different will be these inputs to these multiplexers. So, for the given architecture with 2 flip flops and 2 multiplexers, I can design any 4 state machine. Of course, the combination logic of the output also will be different. The second thing is the design is so simple, I do not have to go through corner map reduction, etc. All I have to do is to direct mapping, that is, I have the state table, I have the hardware, so I match the truth table, the state table to the inputs of this flip flop. That is why it is called an MSI based design. This is a medium scale circuit, MSI stands for, and I already told you in the beginning one of these lectures, these 2 4 to 1 multiplexers can be obtained as a single package. So, we have one package for this, and if you want 2 separate flip flops, you can get 2 flip flops, otherwise you can have a dual flip flop also as a package. So, one package for this, one package for this, and one NAND gate, one AND gate, one inverter. That will be the part count for this problem. Let us move on. We can make it even simpler than this. The next thing we saw was ROM based design. So, can we use now ROM instead of, this is multiplexer based design, mux based combination logic. Let me replace the mux by ROM. It is even easier because we know that ROM is nothing but a hardwired truth table, and truth table is what it is, the state table is nothing but a truth table. So, what I am going to do is to use the same truth table in a present state input, next state output, the same table where this is A, B, X, A plus, B plus, C, 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. That is the state table written as a truth table. That is all. That is as long as the information is same. You call it state table or a truth table. In the case of state table, the information is that the state variable changes based on the present state and the input. That is why it is called a state table. When I call it a truth table, it is the input combination versus the output combination, but the information is same in both cases in here. So, and the output side of the truth table would be 0, 1, 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 0, 1, 0, 1, 1, 0, 0, 1, 1, and 0, 0, 0. Correct? This is the. Now, what I am trying to do is I am going to take this ROM as an input combination logic. I am going to replace my mux using a ROM. Earlier I replaced gates with mux, now I am going to replace mux with ROM. What is the size of this ROM? There are only 3 input variables, namely to the state variable and the input. And for each of these there must be a corresponding next state information and the output information. So, I need to have 8 locations in this ROM. There are 3 inputs and 8 outputs in this ROM. So, it is a 3 address ROM. One of them would be X, B, A. These are the 3 variables to the ROM, input variables. Output of the ROM would be Z, B plus, A plus, and this is a ROM whose size is 2 power 3, there are 8 words, 3 inputs, 2 power 3, and each word has a 3-bit output. 2 power 3 by 8 or so many bits, or 8 bits, 8 into 3 bits. Do not multiply this and say 24 bits, because if you multiply this and say 24 bits, you do not know what is the organization of the ROM. I need to, in fact, the best thing to say is 2 power 3 into 3, but then 2 power 3 is 8, so you can say 8 into 3, 8 times 3. I want a ROM with 8 locations, each of 3 bits width. That is what it means. If you multiply and say it is 24-bit ROM, you do not know how many words, what is the width, we do not know. Now, what happens to the output? The output is fed back into registers, is kept in the registers, and fed back as inputs. These are D inputs, Q outputs. These are ROM based design. Now, this whole thing is to just program this table, this state table if you will, into a hardware and write it into this ROM. So, people do not usually, when they do a ROM design, they do not usually give this table form in this form, because ROM is usually used for designs which are very large, but we are only having 8 words, so we can afford to have this table in this form, in binary form. Supposing I do it in a sort of a very huge design, where there are several inputs, several outputs. If you write the whole thing in binary, the table becomes so large. So normally ROM table is expressed either as a decimal or a hexadecimal information. So what is normally done is each of these is called an address. So ROM address 000, 001, 010. So these are called addresses. And these are called the contents or the word content. What is the address and corresponding content of the word in that address? That is what it is. So we will give an address. So it is called a ROM table. This is not called state table, not called truth table. They call it a ROM table, in which they will give you address on the left hand side and the content of that address. What is the content of the ROM? ROM content, word content or ROM content. ROM content. So it is going to look something like this. You have to draw in a ROM design, you have to give what is known as a ROM content table. The design is not complete until you give a ROM content table. So a ROM content table, you give address and the content of that address. It is not a big deal. All you have to do is to write it in form of a concatenated. Now it's the binary 0, 0, 0, 0, 1, 0, etc. Right? So concatenate them and give it as a word. So for example, in this case 0, 7 addresses are there. And each of these addresses, what is the content? First content is 2, second content is 0, third content is 2, fourth content is 4, then it is 2 again, 6, 3 and 0. So this is the content, that is address location 0 contains information 2. When you code this information 2 into binary, and you decode this information 2 into binary, it becomes 0, 1, 0. That is what we want, 0, 1, 0. For example, location 4 content is 2, let us take some other content. Location 5 has content 6, 5 is 1, 0, 1, that means it corresponds to the 1, 0 state and the input 1, because this is expanded, become 1, 0, 1. First two are the state variables, the next is the input variable. So when state is 1, 0 and the input is 1, what should be the output? 1, 1, 0. That means the next state is 1, 1, output is 0. So all that is concatenated, the information is contained in this ROM table. This is a very simple trivial example. Usually they have many more rows and then they use usually hexadecimal representation. They do not stop with decimal, normally written in hexadecimal form. Normally represented in hexadecimal. Now the simplification is obvious. From gates to multiplexer there is a reduction in the hardware, from multiplexer to ROM there is a reduction in hardware, because the whole ROM table is a one piece, no inverters. In the multiplexer I had to have an inverter, X bar and all that is not there, and extra gates for the output was not there. There is an output Z gate in multiplexer design which is not there in this case. A ROM of the correct size followed by 2 registers, and 2 registers, I mean 2 flip-flops, which can be given as a one single IC. So now I have reduced further. In the next level of simplification of the hardware, that means integrating the hardware, I am reducing the hardware count from the gate to multiplexer to ROM. Even the ROM design we had a ROM and a register which is 2 flip-flops. Now can we integrate the flip-flops also into the hardware? Yes, it is possible, because we have already seen these different versions of the programmable logic devices, PLAs and PILs. These PALs also have registered outputs. We saw when we discussed PALs, we said that there are also possible to have, it is also possible to have programmable logic devices, PALs, with registers in the output. That means the sequential circuit requirement of a flip flop can also be built into the PAL. So, in a single PAL I can now get the whole circuit, the combination as well as the combination logic as well as the registers or the flip flops. So, for that again let us look at this truth table. We will go through the PAL implementation. Again the same state graph I am going to implement using a programmable array logic, which will not only earlier multiplexer based and ROM based only replace the combination logic. Now, this PAL is going to replace the whole thing. There is no combination logic, no sequential logic, nothing. Everything will be put in this one chip when the design is completed. So, for that let us look at this state table one more time. This is the same table we have used again and again. Now, what are the things? I need a next state value for A plus, so that will be the given to one of the flip flops A. Next state value for B plus, that is B plus is the next state value which is be given to flip flop B and the output. These are the three things I am interested in. A plus, B plus and C are the outputs. Now, A plus, this is a combination logic input, 0, A, B, X are the three inputs and A plus is the output. So, you can do a corner map or whatever you want, or you can just by inspection you can write that A plus is 1 when A, B, X are all 1. So, A plus is A, B, X or A, B bar X, A, B, X or A, B bar X. Which means I can now take AX. So, A plus is nothing but AX. So, if I can get this term AX in my programmable array logic, you know that programmable array logic PAL has a combinational part where I can combine the inputs to form any output, and I also have a sequential part where I can store it in a register. So, in one of the combinational gates, if you can get AX, I can get A plus. Now, look at B plus, the second output required is the next state variable B, which is B plus. Look at this pattern, very interesting pattern. This B plus is whenever the X is 0, whenever X is 0, B plus is 1, 0 0, 1, 0 1, again 1, 1 0, again 1, 1 1, again 1. So, whenever X is 0, I get B plus 1, plus there is an extra term here, this term is extra, 1 0 X. So, my B plus would be X bar, whenever X is 0 it is 1. In addition, I have one more term which is A, B bar X. A, B bar X. This is the B plus term, and the output term C is nothing but again A, B, X bar. We have seen this before. So, if we can get these three terms implemented in the combinational logic part of the programmable array logic and have two flip flops to store this A plus value and B plus value and feed them back as A and B in the next clock cycle, then I have implemented the whole thing. And I know fortunately we have flip flops, I mean PALs with combinational inputs, gate structure, flip flops with the output, and also the facility of feeding the flip flop outputs back into the input. So, let us look at a schematic of one such PAL. This is not any specific device type number, usually you go for a device type number. I am giving you the sort of a requirement, practically available PALs are even more complex, will have more features, in fact more combinational inputs, more registers, but I am giving you a minimum configuration required for this. This is not a any practical part available. It is a minimum requirement, sort of a theoretical assumption. I am assuming you have a PIL of this, and it is not an assumption which is not valid, because this, as I said, is a one of the low end requirements for me, whereas even the smallest PIL available in the market will have more features and more capabilities than this. That way I will not be doing anything wrong in assuming this is available, assuming that this is available. So we have this A, x is given to this, and x bar, of course. This is x bar. I have 2 flip flops. There are many registers in the output. I am going to choose 2 of them. One of them Q and Q bar is fed back. This becomes A bar, so I put an inverter, so A and B. So this also acts as an input to the. So these are all the inputs of the combination logic, X, A, B. See, in the combination logic here, I need X, A, B. So I should and X bar, A bar, B bar. Since all of them are required, I need to create all of them here. X, A bar, A bar. Similarly, the second flip flop will have the output B derived here. Second flip flop B, this will be B bar fed here, and this is a clocking, though this flip flop is commonly clock. Now all I have to do is to create this term for A plus, create the term for B plus, create the term for Z according to these equations using the combinational gates available. Z is very easy, it is A B X bar, it is A B X bar. So we have a AND gate. I am not going to show the actual way in which it is drawn in the book. This is enough. So we have a combinational gate. Of course, there will be several AND gates with feeding to an OR gate, and to program it such that you get the output. But I am just, it's a symbolic representation. So I am going to say that I am going to combine, there is an AND gate possibility. So I am going to combine this and this and this and get this requirement. This is only one of the several terms you can put into an OR gate. Actually, in a practical device, there will be an OR gate output. The OR gate will have several inputs. Each of the inputs is an AND gate combination. Coming to the second A plus, that is again very simple. It is A X bar. So I am going to have another AND gate used for this purpose. A X. This is my A plus, which becomes A after the clock. The next state value, present state value. And finally B plus. B plus has two terms, X bar or A B bar X. So I need 2 AND gates combined into an OR gate. So one AND gate, another AND gate. This is only a symbolic representation. As I said, in the practical circuit we will have more AND gates feeding to every OR gate. So we have more flexibility and more possibilities. So this is my B plus becomes B. What are the 2 terms required for that? One is simply X bar. So let us have this X bar as one of the terms, one of the inputs of the OR gate. The other input of the OR gate is A B bar X, which is A B bar X. So A B bar X or X bar together gives me the next state variable B plus. A and X gives you the next state variable A plus. X bar A B gives the next state the output variable Z. So in one IC, which is a programmable array logic IC, having the proper inputs, as given, we can realize the whole circuit. So I have here one PIL in which I will have the following inputs, X C as the output, nothing else, because this A going back will be, is internal. This A going back as input, B going back, these are internals. So, I have the outputs of A and B if required. Of course, I do not require in this case. So, the register outputs are available, but we are not going to use them, and a clock. These are the only inputs I have used. So, the requirement of this PAL is minimum requirement. This is not it is a very, very simple trivial PAL. Any standard PAL that is available in the market will have many more features. So, I need 3 inputs they call it, even though it's 1 external inputs and 2 internal inputs, 1 internal, 2 external. The convention is to call it as 3 inputs, because I should be able to connect up to 3 inputs, whether they are internal or external. So, even though it is a 1 external input, they usually call 3 inputs, and only 1 output is required, but then again A and B are not required, but they are available. So, I should also count them as outputs, 3 outputs, again 1 combinational plus 2 registers. So, this will have the minimum requirement of this would be, if you define it, if somebody asks you, give me the specifications requirement for this design to be carried out in a single PAL, you do not know what is available in the market. Suppose you do not know what is available in the market and somebody asks you to give you a minimum specifications for the design, you will say give me an PAL with 3 inputs, one of them should be internal, one of them is external and 2 internal. I have my students watching here, without informing me I have made a mistake. 1 external and 2 internal, 3 outputs, one of them is combination output for the output Z, other 2 registered for, this is for X input, this is for A plus, B plus. Similarly, 1 combination is for Z, 2 required for A plus, B plus, 2 registered, and then we will have to say at least enough number of OR gates, enough number of AND gates for each of these OR gates. That is not a trivial, this is a very trivial requirement, because I need only 1 AND gate. For X, for Z I need only 1 AND gate, for B I need 2 AND gates, and for A I need again 1 AND gate. So, I need at least 1 OR gate with 2 inputs, and I do not have to have any other OR gate, 3 AND gates should be there, 4 AND gates should be there, out of these 2 of these AND gates should be together, be able to give into OR gate. This is the minimum requirement. Of course, this should be clock input, I will be able to give clock, also should have power supply, VCC and ground. But this is, as I said, I am just trying to go from the other end. I took a very simple problem. In one lecture I want to finish the complete design flow of from the gate level to multiplexer level to ROM to PAL, to show you the gradual reduction in the hardware requirement. Less and less number of pieces of hardware that will be used, circuit become more and more efficient and reliable and easier to implement. That is the purpose of this lecture. So, that is why the trivial example was taken, but in practice we will have these PALs will have much more capabilities. For example, a standard PAL will be at least having 8 inputs, combinational external inputs, 8 outputs, out of them 4 of them may be combinational output, 4 of them will be registered, and these registered output can also be brought back as inputs. So, we will have 8 external inputs, 4 internal inputs as one typical scenario, 8 outputs, 4 of them combinational, 4 of them sequential, a clocking, and each of these combinational outputs will have, or each of these outputs, whether it is a combinational or registered outputs, will have several will have OR gate inputs which can take several AND gates as inputs to the OR gate. So, lots of these things can be will be found. So, you can have make a much bigger design, much more complex design of systems using a single PIL, but I am just giving this gist to you so that in one single IC, now I do not have any registers, I do not have inverters, I do not have gates, nothing. One PIL I go and buy and program it for the whatever I want. My black box is again here. This is my input, output, clock. This is my original circuit. This is my pattern detector. And I need one input, one output and one clock, one input, one output, one clock. These are not used. One single IC, the whole system. The next lecture we will take a bigger design and see how we can fit it into an available PIL. We will stop here for today. Thank you.